So let's get started on 13.3 on arc length. So let's suppose r of t is our function that traces out that curve c there. Put a c there just for fun on some interval. So you could have, t equals 1. Let's do this here. So t equals 1 might be here. Actually, I did like this, huh? T equals a, and then 3, T3, T4, and so it traces out this whole thing. So that's what our curve does. And so what we want to do is define basically what's the length of this curve that's traced out by r of t. So let's define it, look at a couple examples, we'll do a little derivation, and that it'll be it for 13.3. So let's see how long this goes or takes. So first, let me show you the arc length formula. And this goes back to arc length of parametric form, things like that. Okay. So let r of t be a vector valued function with f, g, and h continuous and differentiable on AB. The arc length of r of t from t to t equals a to t equals b is given by this. Okay, so the arc length of r of t from t equals a to t equals b is s equal to a to b, and then the square root of f prime of t squared. So, well, I'll show you the derivation, so just later, but let's just look at the formula and apply it. G prime of t squared, and you go on, you continue, right? Plus h prime of t squared dt. All right, so that basically comes from the distance formula at each little line segment, which we'll go over that in a little bit. If you were to remember this, like if you actually had to memorize stuff these days, you'd memorize that it's a to b, and that actually is just the magnitude of r prime, right? You would just say magnitude r prime of t dt. Okay, so let's look at an example. Find the arc length given by, so find the arc length given by r of t equal to cosine t I plus sine tj plus tk on 0 to 2 pi. So to calculate this, you're going to need r prime, right? So let's just calculate r prime. So r prime of t equal to, so you take each of these derivatives, right? Derivative of cosine is minus the sine. That's going to be cosine, and then just 1. So you get minus sine ti plus cosine tj plus k. And then we need to, so then take its magnitude. You could take it from here, right? So try this, continue, get your result. So r prime magnitude ends up being the square root of, and then it's just sine squared t plus cosine squared t plus 1. So that's just, what's that equal to then? That's just the square root of, well, that's just 1 plus 1, so that's just root 2. So the magnitude is constant on this one. That's kind of a unique case. I know first example is always kind of easy usually. So you get just root 2. So then when you integrate, that's all you get, right? I mean, you integrate, so the arc length of that. Now, what is that anyway? What form is this thing? This guy. What function is that? So that's the helix, right? So it makes sense that you are getting a kind of a nice result because you're basically just going around a circle, and then it climbs at a constant rate of t. So we say, so usually we use s for arc length. So s is the integral from 0 to 2 pi of root 2 dt, which is equal to root 2 times, and then then that's just integral, that's just t from 0 to 2 pi. So that's just 2 pi minus 0, so it's just 2 pi root 2. Okay. So now, let's look at a derivation of this. Okay, so let's take a look. I'm going to go ahead and copy it because it's a little longer than usual. Well, not longer than usual, but I don't want to spend all this time writing down. So I really just need you to grab that, or I'm just going to grab that picture, and then I'll have a few extra things here that I'll write up the rest like I usually do. Okay, so I called this a brief derivation of the arc length formula because I don't go through every little detail. So let's go ahead and write this down. Write in your, so pause the video here and write all this down. So you have your function like this, your axes, and then I put in this generic picture like we do of C, and then you have your R of A, R of 2, etc., tracing this thing out like that. Okay, so this is how we would start it. We would say let C be the curve defined by f of t plus g of t plus h of t ijk. And for t in a, b. Okay, then our goal is to find the length of the curve from A to B. So we want to find that length. So this is how we always start these things. So we're going to let P, so this is going back to Riemann sums. So I'm going to define a Riemann sum and do its calculation. Okay, and again, this is a brief derivation. I'm not going through every little thing, but it's still enough to kind of get us used to how to do this. So we're going to let P be a partition on AB, like that, right? So this is all disjoint intervals from T naught to Tn. And then we're going to define the norm of the partition. So that is the norm of P is the length of the largest subinterval Okay, and so what you're doing is you're taking your interval on the reals, right? This is R. And you're taking A to B, and you're partitioning this thing. Like, so here's T1, here's T2, T3, right? And that's not a uniform or anything, etc. Then we're going to get to t sub k minus 1 to t sub k. And this would be t sub n. This would be t naught. And then we're going to choose some value within the kth interval. And it's not in the middle. I almost hit in the middle. And that's our t sub k star. Or sometimes they pick a different variable, but it's some random one inside that interval. We will look at as well. Let me try this today. We'll look at as well in there the length of the interval. So the length delta t sub k is your tk minus t sub k minus 1. And then we will choose my t sub k star in the kth interval, t sub k minus 1 to t sub k. And then we're going to define the all right, what did I define normal? I'm not sure why I wrote that. Okay. So we choose t in there. And then we apply a Riemann sum. I'll say and apply, or like construct, that kind of idea, a Riemann sum to the length of the line segment connecting. So it's the line segment, the length of that line segment. So line segment connecting r of t sub k minus 1 to r of t sub k. And you use the distance formula. So if you go back up here, we're talking about these line segments. So you're going to be able to define that line segment, that line segment, that line segment, etc. And then that's like how your curve is partitioned. And then as you create more and more of these line segments, when you take as the norm approaches 0, meaning the length of the largest one is approaching 0, you get all these infinitesimals, right? And you end up getting the whole thing. So these line segments aren't as broken up. So you break that now like this instead. Okay, so those are the line segments we're talking about. So you basically calculate the distance formula from here to here. And that is the square root of the sum of the squares at each point. So you subtract the points and take that length. All right, so that's where I'm not showing you all the little details, but it's close enough. Okay, so then you do the limit. So you do the limit as the norm of the partition approaches 0 of the sum over all the k's of the square root of f prime of t sub k squared plus g prime of t sub k squared plus h prime of t sub k squared dt. Delta t, because we're not there yet. So when you do that limit, so that's the part I didn't really show you that. You could go back to parametric forms and look at length of a parametric curve and how that's defined. And it's basically defined by looking at these line segments. You add them up. So to get the length of that line segment, it takes a little work actually, but you have a point P to Q. And to calculate that, you end up getting, essentially it's like the you end up applying one of our important theorems. I think you end up applying the mean value theorem, where you get, if you're going from between 2 points, there exists a value in between such that f prime of that value is the difference, right? Not going to say it all here, but that's what you get. That's why you get those derivatives in there. It takes a bit of derivation. It's actually in Calc 2. Okay, so that's the part I kind of skipped a little bit, save a little time. So look that up. Okay, so I'll just say, how about I do this? I'll just say C distance formula, C parametric in Calc 2. All right, so then once you take that limit, that is by definition, the Riemann sum gives you the integral from a to b, and then the rest is the same. We can actually just copy that. Well, I can, because I'm trying to save a little time as we go. You can fast forward a little bit or pause when you need to. dt. And that, of course, is actually integral a to b. That's just the magnitude of r prime. All right, that's what we just said. Okay, so that's why I called it brief. Okay, so if you want more details, go ahead and look back. Parametric form in Calc 2, deriving the arc length. And I believe I actually either did that or had that or showed that last time in Calc 2. I could maybe look that up and post it. Okay, I'll go ahead and do another video for the next part, which is on a couple other things regarding, let's see, definition of arc length function. We do that, and then we end up getting into the next few things. Okay.